Hi, y'all. This is the start of chapter 2, which is all about linear motion. Another way to put that is motion in one dimension. So we could be talking about motion in the x direction, maybe a runner running back and forth across the ground, or we could be talking about motion in the y direction as well. This could be something like a ball falling, or something similar to that. A jet, maybe not jet, but maybe a space shuttle launching straight up in the air. So in order to talk about these things, we have to introduce the concepts of velocity, acceleration, and we'll also do some graphical analysis of motion. Before we get there, though, we first have to remind ourselves of what displacement is. So displacement refers to change in position. So if I've got some initial position, which I can denote x sub 1 or x sub 0, or what's called x naught, or x sub I, where I stands for initial. And then I've got a final position, which we could call x sub 2 or x sub f, or just plain x. Then our displacement is going to be the difference in our final position minus our initial position. And notice there that those are vectors. So not only do we have size information there, we also have direction information too, and we have to keep that direction information in mind. Oh, the delta there, that triangle means final minus initial. All right, so there's a difference between distance and displacement. Distance is literally just how far you travel. I could be, I'm a runner. I talked about that a little bit. I could, go for a jog and start right outside my house, and I could jog for 5 miles and end up right outside my house, and I would have run a total distance of 5 miles. And now, on the other hand, displacement is not necessarily the total distance traveled. Displacement is just a vector that goes from somebody's initial position to that person's final position, or maybe it's not a person, maybe it's I don't know, an elk, a car, a ball, whatever. Displacement is final position minus initial position, and is a vector. All right, so let's take a look at this idea of position, and we can define some swimmer to be at a position x is equal to 0 meters. Of course, typically we call to the right positive and to the left negative. We can, maybe picture our swimmer swimming out to a position of 4 meters, and then swimming back to a position of -5 meters. I don't know how she swims backwards like that, but go with me. Now, what's the total distance that swimmer has swum? The total distance is 14 meters because she went from 0 to 4. That's 4 meters. And then she went from 4 to -5. And so in doing that, she swam 9 meters. So 5 plus 4 is 9, plus 4 is 13. So 13 meters. That's what do we 13 meters. There we go. Confusing. Apparently, I warned you, I can't add apparently. But the total distance she swum is 13 meters. Her displacement, on the other hand, well, she ended up at this position of -5 meters. She started out at a position of 0 meters. So her displacement would be -5 meters minus 0 meters equals -5 meters. So final minus initial, and so her displacement would be -5 meters. And that -5 meters, that does have both the size and the direction information because we included the negative sign. We're just worried about motion in one direction. So, to the right is going to be positive, to the left is negative. The negative sign helps us to include that direction information in there. This coordinate system, a coordinate system is just a tool. We didn't have to put x is equal to 0 where the swimmer started. Instead, we could have defined x is equal to 0 at a different position. So there we go. Regardless, the swimmer's displacement is still, what is it? It's -5 meters. In this case, her final position would be 0. Her initial position is 5 meters, and her displacement would be -5 meters. So our displacement, there's the same thing no matter what. All right. So what's next here? Concept of constant velocity. What does that mean? That means that somebody's moving at the same speed in the same direction. Um, so um, one example of something that's not constant velocity that we might think is if we've got maybe a circular track and somebody's running around at a constant speed on that circular track. Um, well, if it's a circular track, then the person's direction of motion is constantly changing. They might be running east and then north and then west and then south and so on and so forth. Well, in this case, the velocity is changing. Why? Because the direction is changing, even though the speed is staying the same. So constant velocity means same speed, same direction. And the way we calculate average velocity is just by looking at the displacement divided by the time. All right. Speed, on the other hand, is just physically how fast you're going. So we can think about the speedometer in a car it tells us how fast we're going. Velocity talks about speed and direction. All right, so let's take a look at this example. We've got a jogger that runs 0.15 hours, which is 540 seconds, at an average speed of 2.22 meters per second. We're asked, what's the distance that this jogger travels? So we can see from our equation there that speed is equal to distance over time. If we rearrange this equation, distance is going to be equal to speed times time. And that is, let's see, 2.22 meters per second times 540 seconds is going to give us a total distance traveled of 1,200 meters. All right, there we go. So that's the total distance the jogger travels. All right, on the other hand, we can talk about velocity, and notice here that velocity is what? It's displacement divided by time. So we've got that vector information there, those arrow signs. You see that bar right there? That bar stands for average. So in order to calculate average velocity, it'd be displacement divided by time. Let's take that idea and apply it to a oval track. So let's say that our jogger, who jogged 1,200 meters, was running around a 400-meter oval track. We're asked for the average velocity of this particular jogger. So let's think about the jogger's displacement. If we've got a 400-meter track, there's our 400-meter track, and we think about the number of trips our jogger takes around that 400-meter track. Well, let's see here. Let me change my color of my ink. Say that the jogger starts out right there. The jogger makes one trip around the track, that's 400 meters. Another trip around the track, that's another 400 meters. Another trip around the track, that's another 400 meters. So it takes the jogger 3 trips around the track to make a distance of 1,200 meters. But one thing that you notice is that, well, my jogger started out right there at that point. And where did my jogger end up? My jogger ended up right there at that point again. So my jogger's displacement here, delta x, was, well, let's see, that jogger's initial position was the same thing as the jogger's final position. This is my final. That's my initial. My final and my initial position were the exact same thing. So the jogger's displacement was 0. Well, if that's the case, if the jogger's displacement is 0, and then excuse me, 1 second, need to erase that. Getting ahead of myself. There we go. So if my jogger's displacement is 0 and average velocity is equal to displacement over time, then let's see here. My average velocity is 0 meters. That's 0 meters. Oh, and guys, I'm so sorry for whistling just now. I realized that probably came through the mic really badly. So 0 meters divided by 540 seconds. So my runner's average velocity was 0 meters per second. And that's the answer to this one. All right, we'll do more in class.